Okay, so last chapter we learned how to graph in the standard equation of a circle. So like this being x squared plus y squared equals 9. I know this is a circle centered at the origin because remember it's x minus h. Well, there is no h, so it's 0 squared plus y minus k. Again, no k, so it's 0 squared equals the radius squared. So I should be drawing a circle centered at the origin with a radius of 3. Because again, r squared is 9. But now we're going to graph this like a function instead of just knowing it was a circle. Now the problem with graphing this like a function is it's not a function. If you'll think about the graph of a circle, well, would that pass the vertical line test? No. Okay, so I want to make this into two functions that I can graph the circle in pieces. So again, this is introducing us to the idea of a piecewise function. So I'm going to take this and I'm going to solve for y. So that tells me y squared equals 9 minus x squared. Now y is being squared, so I would take a square root of both sides. When I choose to take a square root, I always account for the plus or minus. So y equals plus or minus the square root of 9 minus x squared. Okay, so really what this is, think about when you solve an equation and you get something like x equals plus or minus 2. Well, that means x could be 2 or x could be negative 2. Well, same idea here. Y could be the positive square root of 9 minus x squared, or y could be the negative square root of 9 minus x squared. And so we're going to graph those two pieces because each individual piece makes a function. So first, we need to figure out what our domain is. What is our list of possible x's? Now we're going to plug in some x values to see what our graph looks like. So again, on the left side for y equals negative x squared, let's see, some x values I might want to plug in. 0. Okay, that would be very interesting. 3 would be interesting, and negative 3 would be interesting. So now if I plug in negative 3, that's going to be the square root of 9 minus negative 3 squared is 9, which is 0. So the square root of 0 is 0. So when I plug in negative 3, I get 0. When I plug in 0, I get the square root of 9, which is 3. When I plug in 3, again, that would be 9 minus 9, which gives 0. So these 3 points are at negative 3, 0, 0, and 3, 3, and 0.
I'm confused. Why didn't you plug in? Normally when we plug in x's and y's, we do like negative 2 and negative 1 and 0. Why didn't we do that?
You can.
We'll just get weird numbers.
No, 1, that would be okay. Yeah, they would be weird y's, I guess. If you plug in 1, you get the square root of 8. So that would be 2 radical 2.
How did you know to plug in the negative 2?
Well, I plugged in 3 and negative 3 because if I plug those in, I get 0. Take the bottom, take what's underneath and set it equal to 0. So x squared is 9, so x equals plus or minus 3. So those are my endpoints. So like if I plugged in 4, I would get 9 minus 16, which would be negative radical 7. So I can't plug in 4. I can only plug in things between 3 and negative 3 that will give me valid real number answers. So this graph, again, think about, you know what it's supposed to be. It's supposed to be a full circle. And when I cut it in pieces like this, I'm going to graph the top half of the circle first. And now over here, I'm going to be graphing the bottom half of the circle in two pieces. Okay, so over here, same idea. Plug in some x's, find the y's. So again, the same thing is underneath the radical, so I want to plug in the same x's. I want to plug in 0, 3, and negative 3. Now if you plug in negative 3, again, you'll get negative square root of 0, which is still 0. If you plug in 0, you get negative square root of 9, which would be negative 3. And then if you plug in 3, again, you get 0. So the graph, negative 3, 0, 0, negative 3, and 3, 0 is here. And so now you'll be seeing the bottom half of the semicircle. And I've turned my one circle graph, x squared plus y squared equals 9, into two pieces that are semicircles. Okay, so now it tells me to list the ordered pairs that satisfy the equation. So you'll see here it's like we've got a table of values. So my x's are going to be 0, negative 5, and 5. And I want to know what y value I get out when I plug those in for 0. So think about plugging in 0 for x. Then we would be left with y squared equals 25. So to find out what the y value would be, I would take a square root. When I take a square root, I always account for the plus or minus. So when I plug in 0 for x, I've got two possibilities. I could have positive 5 or negative 5. Now if we plugged in negative 5, what would happen? Well, y squared equals 25 minus negative 5 squared. So that would be y squared equals 25 minus 25. Y squared is 0. You take a square root. You take a square root, you always account for plus or minus. But there is no such thing as plus or minus 0. There's only 0. So when I plug in negative 5, I only get one possible value, that is 0. And then plugging in 5 is very similar, because when we square it, we're going to get the same value. So that would be 25 minus 25, which again is 0 for y squared. Take a square root, plus or minus 0, but again, doesn't make sense. So when I plug in 5, the y value is 0. So we're going to take a little more in-depth look at the absolute value of x function. So it says make a separate table of ordered pairs for the piecewise function. Graph the functions on the same coordinate plane. State the domain and range of the entire piecewise function, considering the separate graphs as if they were one combined graph. So really, what is y equals the absolute value of x? So what does an absolute value function do? It makes whatever comes out of it positive, okay? So if we think about defining it as a function, the function f of x equals the absolute value of x. So really, there are two things that could happen. What if my x value was greater than or equal to 0? So again, that would be 0 and positive numbers. Then what I put in for x is the exact same thing I get out. If I take the absolute value of 3, I get 3. Take the absolute value of 8, I get 8. So right here, the first piece of my function is if f of x equals x if my x value is greater than or equal to 0. Now the second possibility is x could be less than 0. That means x is negative. So what happens when I plug in a negative value into the absolute value? We make it positive. So essentially what we're doing is we're changing the sign of the negative number. So if I plug in a negative x value, then the y value that comes out is negative whatever x is. So you see how I've got two pieces that the graph is defined for. So we look at the restrictions, which are here, to know which piece I plug it into. If my x is greater than or equal to 0, I plug in here. If my x is less than 0, I plug it in here. And so now that we've got this absolute value function defined as a piecewise function, we want to graph each piece of the function. So the first piece is f of x equals x if x is greater than or equal to 0. So what are some x values that fit this criteria? Well, we've got 0, 1, 2, and 3. All of these fit the criteria of x being greater than or equal to 0. So let's see what happens. If I plug in 0 for x, that goes here, then my y value that comes out is just x, which is 0. If I plug in 1, again, that fits here. My y value is just 1. If I plug in 2, it's 2. If I plug in 3, it's 3. Now we're looking for x's that are less than 0. So will 0 actually be included in that graph? Is 0 less than 0? No, it's not. So the point 0 does not actually count in this graph. But all the way up to 0 does count. So like negative 0.000001 is valid. Negative 0.00000001 is valid. So to signify that, we're going to plug in 0 because we can get all the way up to 0 without including it. And we put that open circle around it so we know that this is actually not a point. But everything leading up to it is a point. So if I plugged in 0 there, well, this time we're looking for x being less than 0. So again, we'd plug it into this piece of the graph. So negative 0, again, would just be 0. Now if I plugged in negative 1, so again, x is less than 0, so I'm plugging in negative 1 here for x. So I would get negative 1. Well, negative is the same thing as positive. So when you plug in negative 1, you get out 1. Same idea, plugging in negative 2, negative 2 gives positive 2, and negative 3 gives positive 3. So I'm going to graph this left side here in red. So again, my lowest possible value is x being greater than or equal to 0. So that's included, so I'm going to put a closed circle there. And then we've got 1, 1, 2, 2, 3, 3. And so in the right direction, that is the line of the graph. The graph looks like y equals x. Now on the left side, the graph is going to look like y equals negative x. So again, you can plug in these values. So 0, 0 is not included. So we would put an open circle around 0, 0. Okay, but you see that same point is closed in by the other side. So the open circle doesn't really matter in this case. It's still good to get in the habit of that. Then negative 1, 1, negative 2, 2, negative 3, 3. Then we graph it in this direction. Okay, and that's our parent function that we looked at last week. Now it tells me to identify the domain and range of this piecewise function. So we're looking at the entire thing. So the domain is the list of x values. Well, the graph goes forever towards the left and the right, so the domain would be all real numbers from negative infinity to positive infinity. The range is the list of y values. So the lowest possible y value doesn't happen until we get to 0, and 0 is included, so I put a bracket, and then the graph goes up forever, so the highest y value would be positive infinity. So you'll see if you had to graph on a graphing calculator y equals the absolute value of x, most of those older graphing calculators do not have an absolute value function, so we would actually graph it in these two pieces, like this, with the domain restriction. And if we could share graphing calculators, I would let you see that, but 2020. Next, we've got f of x equals 3 if x is less than 2, f of x equals 1 if x is greater than or equal to 2. So now I've got two pieces again. Now, in the previous problem, those pieces divided when x was 0. You'll see that was my dividing point. I call that my critical point. Right here, the pieces divide when x is 2. You'll see I have a certain set of rules for x being less than 2, and I have a certain set of rules for x being greater than or equal to 2. So if I was having to work this problem from scratch, I would say this 2 is my critical point because the graph changes at 2. So when I'm making my table of values, I'm going to separate them there for x being less than 2 and x being greater than or equal to 2. So what are some x values that are less than 2? Well, they plugged in 2, 1, 0, negative 1. All those are less than 2. So what would I get out if I plugged those in? So pay attention to this because people mess this up all the time. So first, let's just plug in 1 because the 2 is the special case. 2 is not really less than 2, so we'll save that one for the end. But let's start with 1. If I plugged in 1, that is x less than 2. So that would fit into this category. If x is less than 2, this is the y rule. This is my function. So if I plugged in 1 for x, what is the y value? 3. What if I plugged in 0 for x? 3. There's nowhere to plug this x in. It is a horizontal line. Right? F of x equals 3. That's y equals 3. It's just a horizontal line. And same idea, if I plugged in -1, I would get out 3. Now again, I can't actually plug in 2, but I could plug in all the way up to 2. 1.99998, right, would be a value that would work. But I don't want to plot all the way up there, so let's just pretend like I could plug 2 into here. Well, if I plug 2 into here, I would get out 3. So the graph is going to get really, really close to this point 2, 3. But to show that it's not included, we're going to put an open circle there. So let's graph that portion of the graph. So I go to -1, 3. I plot a point. 0, 3. 1, 3. And then at 2, 3 again, that's not included. So we're going to put an open circle at 2, 3. And the graph goes all the way up to that open circle. And so that would be the first piece of my function. Now the second piece happens when x is greater than or equal to 2. So again, we're going to think of some x values that fit that criteria. Again, we start with the critical point of 2, and then greater than or equal to 2 would be 3, 4, and 5. And then same idea, if I plugged in 2 to this piece of the function, I would get out a 1. If I plugged in 3 there, again, same thing, I would get out a 1, 4, 1, 5, 1. So this time I would go to 2, 1. That is included in my graph because it's greater than or equal to. So I would put a closed circle at 2, 1. What is happening? There it goes. And then plot the other points, 3, 1, 4, 1, 5, 1. And we will continue in the right direction forever. So again, you do a better job making that look like a closed circle than what I can do with this screen. So this is what this piecewise function would look like. Now the domain, what are the x values? Well, let's see, we've got x's, they're happening all the way in this direction, this direction, this direction. Then the x's stop, but they jump to here. So is there actually an x that's not included? No, right here is not included, but it is included here. So the x values go on in both directions forever. So the domain would be from -infinity to +infinity. Now next is the range. What y values does this graph take on? Well, there are no y values that happen here. The lowest y value that happens is 1. And then do we use every y value between 1 and 3? No, we just use 1 and we just use 3. We don't use anything between them. So my range is actually 1 and 3. Just like that. Not in parentheses, not included, not excluded. Because there is no interval of y's. There are only 2 y's. 1 and 3. Okay, so here's a more typical looking piecewise function. That last one was a special case where they both were horizontal lines, which can happen, but again, this is what the majority of piecewise functions look like. So my graph, my function is defined as 5 minus x when x is less than or equal to 2, but it's x plus 1 when x is greater than 2. So again, when I'm making my table of values, I'm going to let it hinge on this 2 being my critical point, because the 2 is the changeover from the first function to the second function. So what are some x values that are less than or equal to 2? Well, you'll see right here they plugged in 2. That is not less than or equal to 2. So we've got 2, 3, 4, 5. That does not work. So let's change that. What are some x values that are less than or equal to 2? 2, 1, 0, and negative 1. If you want to make your own table, whatever you want to do.
Why did they mess up their table?
Well, because, okay, so moving on from here. Looking for x values that are less than or equal to 2. So we found some x values, 2, 1, 0, and negative 1. Now what if I plugged in 2 to the function? Well, again, that would go in up here. So if I'm plugging in 2, what would the y value be? It would be 5 minus that 2, which gives 3. Now if I plugged in 1, well 1 is less than or equal to 2, so again that goes here in the first line. So 5 minus that 1 would give 4. If you plug in 0, you get 5. If you plug in negative 1, 5 minus negative 1 would be 5 plus 1, which is 6. So right here are my 4 points that I found on my graph. There are more. Those are just 4 that we have identified. And so we're going to graph those. So let me get some tick marks going here. Okay, so I go to 2, 3. Now that point is included, so I'm going to put a closed circle at 2, 3. Then I'm going to go to 1, 4, 0, 5, negative 1, 6. And I see the graph is going in the left direction because that's x's that are less than or equal to 2. And it's going to go in that left direction forever. So I put an arrow to signify that. Now the second piece of my function occurs when x is greater than 2. So again, it goes all the way up to 2, but it does not include 2. So we put that open circle around 2 to help us remember, hey, we're going to put an open circle on our graph. If I plugged in 2 here, I would get 3. Because again, we're plugging into this bottom function. Now again, 3, which is bigger than 2, would go here. 3 plus 1 would give 4. 4 plus 1 is 5. 5 plus 1 is 6. So I graph those points. So I go to 2, 3, which is a shared point, right? So we put an open circle. It's actually in the exact same point this time. Again, that doesn't always happen, but this time it did. And then we go to 3, 4. Put a point. 4, 5. Put a point. 5, 6. Put a point. So the graph will look like this. So this looks very similar to our absolute value function that we had earlier, except for now it's been shifted right and up some. Right, but it's got the same properties where the closed circle and open circle end at the same place. That's wonderful. How in the world would that not tie that together? That's going to be fun all the rest of this time. Okay, so now what is the domain? So the domain is a list of x values. So I'm looking left to right. There are no gaps in this function. So the domain would be all real numbers from negative infinity to positive infinity. Next we identify the range. The range is the y values. So the lowest y value that this graph has is 3. It is included, so it's in a brace. The graph goes up forever to positive infinity. Close the parentheses. Okay, so that time we had 2 lines. This time we're going to have one that's a square root and one that is a line together. Okay, so let's look. Now then, my first piece, f of x equals the square root of x plus 2, is only good if x is between negative 2 and 2. So we would say negative 2 is less than or equal to x, is less than or equal to 2. But I like to read it from the center. So x must be greater than or equal to negative 2, but it must also be less than or equal to positive 2. So again, I've got to find x values that fit that criteria. So it's got two critical points that I have to make sure I include. Negative 2 and positive 2. So you'll see we have both of those points. And then we have some points between them. Negative 1, 0, and 1. So let's see what happens to my graph when I plug in these values. So if I plug in negative 2, the square root of negative 2 plus 2 is 0, and the square root of 0 is 0. If I plugged in negative 1, the square root of negative 1 plus 2 would be the square root of 1, which is 1. If I plug in 0, I'll get 0 plus 2. The square root of 2 is an ugly number, radical 2. If I plugged in 1, I'll get the square root of 1 plus 3, which is radical 3. If I plugged in 2, the square root of 2 plus 2 is the square root of 4, which is 2. So really, if I were graphing this, I'm graphing it on these 3 points. Negative 2, 0, negative 1, 1, and 2, 2. I know those other ones are going to fit in there with them, but I don't know exactly where radical 2 and radical 3 are. They're not nice points. So if I graph this, again, let me get some tick marks down. Okay, so I'll go to negative 2, 0. I'll plot that point. Then I'll go to negative 1, 1 and plot that point. I guess I need some y tick marks as well. And then 2, 2 would be here. Now just double check. Negative 2, 0. Should that point be included, a closed circle, or excluded, an open circle? Well, x can be greater than or equal to negative 2, so that point should be included, closed. And then same idea at 2, less than or equal to 2, so this point should also be included, a closed circle. And so we'll see that graph has that general square root shape. I did not draw that very well. Let me zoom in. That looks almost like a line. Okay, this is not a line. This should look like a slight curve, right? Kind of like the parabola. It does. That's what the square root function looks like if you look back on your parent functions. That's better. Now the second part is a line. F of x equals 4 minus x. So x's have to be greater than 2. So 2 is not included, so we put an open circle. But we do want to know what happens all the way up to 2. And then we have 3, 4, and 5. So if I plugged in 2, 4 minus 2 is 2. Again, they're making them match up. That's not always the case. If I plug in 3, 4 minus 3 is 1. 4 minus 4 is 0. 4 minus 5 is negative 1. Then I'll plot those points. So at negative 2, 2, I would have an open circle. I'm sorry, at positive 2, 2. I would have an open circle. Then I go to 3, 1, 4, 0, 5, negative 1. Again, this graph is going to look linear. It should be a straight line. And now there is no boundary on the right side of this graph. X is bigger than 2 would continue to go in the right direction forever. So looking here, identifying the domain and the range. The domain is the list of x values. So again, this graph stops here. It doesn't have any more values that go to the left here. So the lowest x value is at negative 2, and it is included. And then the highest x value, well, the graph goes forever in the right direction. So it would be positive infinity. Next, we look at the range. So the lowest y value, well, this graph is going down forever, so it would have no lowest y value. So that would occur at negative infinity. And then the highest y value, well, the graph reaches its maximum value here at 2. never goes above that, and that 2 is included. Okay, so now we are given the graph of a piecewise function, and we're having to write what it is. Okay, so I'm going to look at this graph, and I can identify how many pieces there are just by looking. There should be 2 pieces. There's this piece on the left, and then this larger piece on the right. So when I'm building my function, I know it's going to be f of x equals, I know there's going to be 2 pieces. There's going to be one up here and one beneath it. You don't have to put that line, I'm just doing it so we kind of keep track. Now to me, the easiest thing to do is identify the x boundaries, which is the end. You know, it says f of x equals something if x is something. And then it's something else if x is something else. So right here, what is the x value that changes the function? Well, the x value changes here at -1. You see the graph is going fine until -1, and then it jumps, and then it starts going fine again. So the critical point where the graph changes is when x is -1. So now it looks like something if x is less than -1, and it looks like something else if x is greater than -1. Now again, we go back to the graph. One of these should be included, and one should not be included. So we'll see x being less than -1 has an open circle, so it's not included. Here, x is greater than or equal to this one because it's a closed circle. So that should be, I don't know what I said, that should be x greater than or equal to -1. So on this bottom one, we're going to make this x be greater than or equal to -1. And again, to me, that's the easier thing to do, so I like to do it first because it helps me identify my boundaries. Now, the next thing, we have to get an equation. Oh, no. Why would that not tie to that? Okay. We've got to get an equation for this part of my graph. So I know it's a line. They're really nice to us with that. So how can we find the equation of a line given 2 points? Well, we know about point-slope form and slope-intercept form. In both of those, I need to know the slope. So what would the slope of this line be? Well, it goes down 1, right 1, down 1, right 1. So I know that the slope of that is -1. And now I know a point on that graph. I know a point and the slope. I'm going to put it in point-slope form. Y minus y1 equals m times x minus x1. So minus -1 would be +1. Now we got to get y by itself because piecewise functions have the y isolated. So we distribute -x minus 1. And then we move this -1 over. It becomes positive. So that would be y equals -x minus 1 plus 1. So it's just like that. So the first piece would be f of x equals -x if x is less than 1.
It would also work to do the absolute value of x if you wanted to. It would do the same thing. I just put absolute.
Now looking at this one, the slope is +1 and the y-intercept is -1. We already know both of those in this graph. We know the slope and the y-intercept. So y equals mx plus b. Well, the m is 1. So it would be 1x, and then the b is -1. So we could write 1x minus 1, or that's just the same thing as x minus 1.